For today's video, we're going to talk about graphing radical functions. So for example, we have f of x equals square root of x. This one is the parent function. It's kind of where everything begins for square root functions. Remember, the square root of x is also the same as x to the 1/2. So both of these graphs are going to look the same. And what we want to think about is what values can we plug in? What values are we going to get out? What is this graph going to look like? And when we're taking a square root, we can only take the square root of things that are greater than or equal to 0. Okay, so for example, if I plug in 0, what is the square root of 0? Well, it's 0. So I'm going to have a point at 0, 0. Okay? If I plug in 1, what's the square root of 1? It's 1. So I have a point at 1, 1. Okay? For 2, I can plug in 2. I'm allowed to plug in 2. And if I plug in 2, what is the square root of 2? Well, it's like 1.414, and it goes on. So it's not like, a pretty number, but we can plot it 2 and then like 1.4 about there. Okay. So instead of just choosing any number we want, it might be best to think about numbers that have square roots because that will help us get like the picture that we want. So for example, 4, I know the square root of 4 is 2. So I'm going to go over 4 up 2, and that's going to be like a nice point on grid lines. And then the next one I know is 9, and the square root of 9 is 3. So 9 comma 3. Okay. And this graph starts at that 0, 0 and only goes to the right from there. Okay. If we're talking about real numbers, we're not allowed to take the square root of like -1 or -5. A square root of a negative is when we get imaginary numbers. And so it's important that we note that the domain of this graph is x greater than or equal to 0. And it's because whatever we take the square root of has to be greater than or equal to 0. We can't take the square root of a negative. Okay, so it's only starting at that one dot and going to the right. And then in the same way, because we can't take the square root of negatives, we're not going to get negatives as our answers. So if we just have the regular square root, notice it's only going up. So from that 0, 0, it's only going up. So we have y greater than or equal to 0 for our range. So that's our parent function. From there, we can shift it left and right, move it up and down, do all kinds of things. And so that's what this table is talking about, how we do those shifts. And we talked about these back with parabolas. We talked about these with some other functions that we've used along the way, absolute value, cubics and things. We've shifted them left and right. We've shifted them up and down. Okay. So just a reminder, the shifting left or right happens inside the square root. So if we're going to if we have like x minus 2, remember it's going to the right, x plus 3, it's going to the left. And those are things that are happening inside the square root, goes left or right. For vertical shifts, that means it's shifting up or down. This thing is happening outside of the square root. So if we have a +7, we're moving up 7. And if we're having, -1, it's moving down 1. And when we're talking about those shifts, what I think of is that point 0, 0 is shifting. And then from there, our shape is still going to look similar. All right, reflecting. So because we have this little piece of something going on, this little graph, this function, we could flip it upside down so that it's going like over, we call it flipping it over the x-axis. And that's when we have a negative out front here. We're flipping over the x-axis. We did these ones before. It was like when we had a right side up parabola or an upside down parabola. We had a negative out front, and that's flipping it upside down. Okay, because this piece only goes to one arrow direction, we can also shift it or flip it over the y-axis. And this is if we have a negative on the inside. Okay, so the one we're used to is flipping it upside down. That's the negative on the outside. Think of the outside being the Y stuff, either moving up or down or flipping up or down. And the inside being the left to right, either shifting left or right or flipping left or right here, reflecting. And then the last thing we can do is stretch or shrink it. So we can make this thing kind of get taller or shorter, depending if we're stretching or shrinking. Okay, so I'm going to take a minute here to maybe use some of those things we know and match the graph to this little A, B, C, and D on the side to which function rule it is. So why don't you pause for a second and try and match them up? Okay, so we should see that if we have x plus 2, this means we're moving left 2 units. So instead of our like kind of vertex point being at 0, 0, we should be moving left 2. So that is the graph A. Because it is shifted and now starting at -2, our x values, our domain is less than or equal to -2, but our range is still greater than or equal to 0. So it starts at 0 and goes up from there. Okay. For number 2, this one is moving right 2 units. So we're going to start at the point 2 comma 0 over here on graph D. And so our domain is only going to the right or greater than +2, and it's still going only up from 0. Number 3, we have 2 shifts. We have something going left 2, and we have something going down 2. And so that is option B, that it is going from the 0, 0, it's going left 2 and down 2. So its point there, kind of starting point, is -2 comma -2. And so that means my x value is going to be greater than or equal to -2. And also my y value from that, vertex, it's going up from -2. And then our last one has a negative out front. The negative out front means it's going upside down, or we say reflecting over the x-axis, and then also left 2. Okay, and so that's what we see on number C. Instead of going upwards, this one is now going downwards, still to the right. So we have graph C. For this one, we're starting at that -2 and still only going to the right. So x is greater than or equal to -2. But for my y's, I'm not going up, I'm going down. So y is going to be less than or equal to 0 because it's like top point is 0 and it's going down from there. Okay, so we can graph these square root functions that have transformations, not just our regular square root function. So we have this first one, number 1, says 1/2, and then the square root of x plus 5. So first we want to notice what are the transformations that are happening. So the 1/2 out front is going to be like a shrink of 1/2. It's going to end up being 1/2 as tall as it was before. So a shrink of 1/2. And then the plus 5 on the inside of the square root is going to be a shift left of 5. Okay? So instead of our graph starting 0, 0, like a normal one, we're shifting left 5. So our first point is going to be over here at 0 or at -5 comma 0. And so if we want to make a little chart of our x's and y's, a good place to start is kind of where we know that vertex point is going to be. That instead of 0, 0, we've shifted left 5, so -5. And if I put 0 there, but the reason it's 0 is if I plug in -5 to my equation, I get -5 plus 5, the square root times a half. So I get half times 0, which is 0. Okay, so that's where that point actually comes from, -5 comma 0. When we're choosing things to take the square root of, it would be best to choose things that I know have square roots, like nice whole number, like perfect squares to work with. And this might come with some practice, but we want to choose numbers that work. So when I plug it into this graph, when I'm plugging it in here, I want to be able to take the square root. So I plugged in -5, that would be the square root of 0. If I plug in -4, then I'm going to have the square root of 1 because -4 plus 5 is 1. And so I have 1/2 times 1. So I end up with 1/2. So -4 comma 1/2. But what I'm thinking about is what can I take the square root of? So I can take the square root of 0. I can take the square root of 1. I could take the square root of 4. Okay. If I want this highlighted section to be 4, I need to plug in -1 into my x value. So if x is -1, I'm going to have my 1/2, but then the square root of 4. Well, square root of 4 is 2. So I have 1/2 times 2, which is 1. So -1 comma 1. So I've already said I can take the square root of 0. I can take the square root of 1. I could take the square root of 4. I could take the square root of 9. Okay. 9, in order to get that highlighted section to equal 9, I need to plug in 4 for x because 4 plus 5 is going to give me 9. So let's plug in that one. So I have 1/2 times the square root of 9. So it's 1/2 times 3, which is 3/2, or 1.5 if you want to put it in decimals. So +4 comma 1.5. And that's good enough. Those 4 points are good enough to kind of get our little square root function. Notice here from the original, we have shifted left 5. That's because our starting point is 5 over. But also this thing is like half as tall. You know, when we were multiplying half times each of those things when we were doing our calculations, it ended up being half as tall. So this one is shorter than our original. Kind of squished down is the way we think of it. Okay. From there, the domain and range, x is going to be greater than or equal to that -5, using the starting point as what we're using. And then our y values are greater than or equal to 0. Again, that starting point is what we're doing. Okay. And then just a word, this function, 1/2 times the square root of x plus 5, this would be the same as 1/2 times x plus 5 to the 1/2 power. Okay. I just want us to be continually thinking that a square root and a 1/2 power are the same thing. Notice where my parentheses are. The parentheses would be around whatever is under the root, under that radical. Okay, so if I saw the problem as a radical or if I saw the problem as a rational exponent, both would be graphed the same way. All right, let's try number 2. This time, what's kind of happening? What are our transformations? So I definitely see this +2 out here. That is a shift up 2. So instead of starting at 0, 0, where we normally did, we're shifting up 2. The negative inside the radical means we're reflecting over the y-axis. We're reflecting sideways. So it's not flipping upside down, but it's flipping sideways. So we say it's a reflection. I guess you could say sideways, but really we'd say over the y-axis. Okay? So our starting point is this point 0, comma 2, because I've moved up 2, 0, and then up 2. But our graph is going to be going kind of this way. We're going to find the actual points, but that's what we're looking at. So when I'm choosing numbers to take the square root of, like if I take the square root of 0, if I plug in 0 for x, I do get square root of 0 is 0 plus 2. Well, that's 2. Okay. If I plug in positive numbers, positive 1, then I'll be taking the square root of like -1 because there's a negative x in there. So I actually can't plug in positive numbers because I can't take the square root of negative things, that minus sign inside. So instead, I want to plug in a negative number. So for example, -1. If I plug in -1, then I really have the square root of -1. Well, that's going to be +1, and then +2. So when I plug in -1, I get +3. Okay. And again, I want to choose things that I can take the square root of. So I can take the square root of 0. I can take the square root of 1. So that's why I plugged in a -1. I could take the square root of 4. Well, in order to get a 4 in this square root, I need to plug in -4. So if I plug in -4, I'm going to have the square root of -4 plus 2. So this is really the square root of 4, which is 2, plus 2. And so we get 4 overall. So -4, comma +4 is another point on our graph. And one more, we can usually take the square root of 9. Well, in order to get 9 in that highlighted area, I have to plug in -9. So I have -9 plus 2. Well, the square root of 9 is 3, and 3 plus 2 is 5. So -9, comma 5. And we can get a good little square root function from there, that I'm starting at this point that's up 2, and then I'm going to the left from there. Okay? So my domain this time, we're starting at 0, like 0 is our x value we're starting at. But instead of going to the right, we're going to the left. So for this one, we have x is less than or equal to 0 because we're starting at the 0 and going to the left. And then for y is starting at 2. It starts at about up 2, and it's going up from there. So y is greater than or equal to 2. Okay, so those are square root functions. You need to be able to describe the transformations, list the domain and range, and come up with a graph. Cube root functions are another thing we want to take a look at. And cube roots can be taken of negatives. So for example, some things we know, I'm gonna make a table first, actually. And I'm gonna start in the middle of my table. I'll fill it in both ways. But if I plug in 0, the cube root of 0 is 0. Okay. 1, I know the cube root of 1 is 1 because 1 times 1 times 1 equals 1. Okay. The next one I know is 8. If I take the cube root of 8, I'm not cubing it, I'm taking the cube root of 8, I get 2. Okay. So far I have 0, 0, I have 1, 1, and I have 8. Oh, that's 9. 8, 2. Okay. But like I said, I can also use some negatives. So if I have -1, the cube root of -1 is -1. So -1 is a point. And then -8, I'm saying the cube root of -8, well, that's -2. Okay. So for cube roots, it's not just going in one direction, it's going all the way from left to right, kind of across our graph there. Okay. On this one, there are no transformations. We didn't shift left or right. We didn't shift up or down. This one is actually the parent function for x cubed, or the cube root of x. And I do want to point out, just like our um, square root, we can either look at it as a cube root or to a 1/3 power. Those things mean the exact same thing. And so this graph represents both of those. We didn't shift it at all. We're just like, that's the original. For the original, domain is all real numbers. I can put in positives, I can put in negatives, goes all the way to negative infinity, all the way to positive infinity. So we could say, X is all real numbers. And the same is true for Y, that Y, even though it looks like it's just stuck in the middle, it really does go all the way down. It's just going down kind of slowly and all the way up, even though it's slowly. So all real numbers for Y as well. Okay, so a square root or an even root, whether it was a fourth root or a square root, is limited only by positive things that we can plug in. But a cube root is not limited. It's all real numbers, left to right, up and down. Okay, and those transformations apply to cube roots as well. So when I'm looking at this number 4, I want to notice the transformations. Okay, a -3 inside of a cube root means we're shifting to the right 3 units. Shifting right 3 units. So instead of this point that's normally at 0, 0, shifting to the right 3 units. So that midpoint where it kind of curves from going up to going up a little stronger is now over 3 units. And then in front, we have two things going on. We have a negative and we have the 2. So we kind of want to list those separately. The negative means it's going to be flipped upside down. A negative in front is saying we're flipping upside down. So that is a reflection over the x-axis. And that is, like I said, upside down. That's the negative part. The 2 is saying it's going to be stretched out. It's going to be twice as tall. So stretch by a factor of 2. Okay. And we're going to make a table, but before I make a table, I just want you to visualize like these things happening. So we're going to reflect over the x-axis. So instead of being down and then up, I'm going to take that away. It's going to be like up and then down. So it's going to look that kind of way. That's what a reflection will look like. And then it's going to be twice as tall. So originally when it would have been like 1 here and 1 here, it's not. It's going to be twice as tall on either side as we go. But we'll make a table of values and actually get the x's and y's. Okay, so I want to start with this midpoint value. The midpoint value, when I plug in 3, notice I'll get a 0 underneath. So kind of working on that radical, -2 times the cube root of 3 minus 3. So 3 minus 3 is 0. The cube root of 0 is 0. -2 times 0 is still 0. So that's this original point. When I plug in 3, I get 0. From there, I want to think of other things that I can plug in. What can I plug in that actually has a cube root? So example, cube root of 1. A cube root of 1 is going to be 1. So in order to get 1 in that highlighted area, I need to plug in a 4. Okay, if I plug in 4, 4 minus 3 is 1, and the cube root of 1 is 1. So I have -2 times 1, and so I get my point 4 comma -2, kind of like we were describing earlier. The things I know cube roots of that are small, 0, 1, and 8. The cube root of 8 is 2. So what do I need to plug into the green highlighter to get 8? Well, if x is 11, I know that's slightly off our graph, but just to see it, if x is 11, then 11 minus 3 is going to give us 8. So -2, and I have the cube root of 11 minus 3. 11 minus 3 is 8. The cube root of 8 is 2. So I have -2 times 2, which is -4. So over here at 11, I'm going to have -4. So kind of right off the graph there. Remember, I can also do cube roots of some negatives. So if I had a -1 underneath my green thing, that means I would have a 2 for x. If I plug in 2, 2 minus 3 underneath that square root is -1. The cube root of -1 is -1. So I have -2 times -1, which ends up being +2. So 2 comma 2 is a point on my graph. And then we'll do one more. What would make the underneath green part -8? Because I know I can do a cube root of -8. So in order to get that green part -8, I'm going to plug in -5. Okay. If I plug in -5, I still have that out front. Plug in the -5. -5 minus 3 is -8. The cube root of -8 is -2. And then I have the -2 out front. So -2 times -2 is +4. So the last point I'm going to plot here is -5 comma +4. And that's kind of enough for me to get this little squiggle graph that goes smoothly through those points that we tried to do. Okay. Notice our graph goes all the way left and all the way right. So our domain is all real numbers. And it's going to eventually go all the way up and all the way down. So our range is also all real numbers. Okay. These graphs can look like roots, or they can also look like exponents. So, a cube root is also a 1/3 power. So whether I have p of x equaling the root or p of x equaling this rational power, 1/3 power, those graphs are going to be just the same. Okay, hope that helps. Good luck.